the first question, which is worth points. I have to review it. I don't know how it's going. It's just like one's like file character right there. Like those are super easy.
Okay, but structure looks right. Okay. Thank you. Okay. Okay, so let's get started. So the project proposal is still under review. Hopefully by Wednesday we'll get back some feedback if needed on those. So if you haven't, a lot of you have started looking at the second homework assignment on the document hash. It's due a week from tomorrow. So you still have, a week from Wednesday this week. So you still have time, but don't wait till the last minute. It should be a bit more than the first homework, but not drastically more, I don't think. Right? For people who've looked at most of it. Okay, good. That's the impression I've gotten from past years with similar homework. So, okay. So today we're going to start the section on class on clustering. We'll have 3 lectures here, and there's one little piece from the lecture on last week Wednesday we didn't quite finish, so I think I'll put that in at the end of the lecture today, and that's some geometry about high dimensional space, which gives some intuition about why these KD trees started to fall apart in high dimensions. But I think that'll be better at the end of the lecture. All right, so we're going to be talking about clustering and in general hierarchical, collaborative clustering. And so, I'll start in a second by kind of trying to define what is clustering and why is how should we think about this problem, right? And trying to lay this out formally. But before I start, I kind of want to start with some warning. I've pre-written it up here that kind of like clustering. There are literally thousands, tens of thousands of different published, peer-reviewed research papers on clustering, proposing different types of clustering, different variants on the core algorithms and techniques, saying different things about them. And really, the thing to keep in mind is when data is easily clusterable, which I'll define, I'll try and give you intuition of what that means. That's kind of a little bit nebulous definition, but when it's easily clusterable, most clustering algorithms will work quickly and will work well. We'll do a good job of finding the clusters. If data is not easily clusterable, then no algorithm will do a good job of finding clusters. Okay, so I'll come back and kind of when we talk a little bit more, to be more precise, I'll maybe kind of give some examples of what this means. But so we're going to spend 3 lectures on this, even though it's kind of maybe one of the core central things people think about when they're thinking about what is data mining, they think clustering. Well, we're going to try and cover kind of a very broad sweep of this area. We're not going to touch everything, but for most things, most algorithms work well if it's possible to cluster data, and if it's not possible to cluster the data, clustering is a bad way to just summarize the data, then nothing you do is going to work. Right? So in some sense, it shouldn't matter too much. Okay? Now, you can talk to other people who are maybe researchers in this area, and they might disagree with me on this, and I would disagree with them about that. But you know, I see people a lot of times trying to cluster data which there aren't any well-defined clusters in it, so it doesn't make any sense. Or they'll try a bunch of different algorithms and they all work. You know, it's not surprising to me. Okay, and we'll talk about, there are some differences in what different algorithms can do. And there's some efficiency differences, and sometimes you need to kind of model the data differently to get in the right form. And so there's still some kind of things that you need to know about this to do it correctly. And if you want to know more than 3 lectures on this, Suresh occasionally teaches a full semester class on clustering where you can learn much more about this. But we're going to do three lectures, and I think this covers probably 90% of all types of clustering you'd ever try and do. Arguably even more than that. Okay, so let's start by saying what is clustering. Okay, so we're getting into a part where we're going to say we're given as input, we're going to give in some 2 things, a data set X. Okay, so this data set will have a bunch of data points in it. Xn, so it's got n data points in it, and we're going to have some form of a distance, which is given as part of the input. In general, we'll say that this goes from, say, x cross x to r. It could be that x is subset of some metric space. Think of this as, let's say this is Euclidean space, and then maybe the distance is more generally defined between not just the data points, but this whole metric space. So think of this isn't RD, just R. So think of it, you could have a distance defined by 2 points, by 2 vectors. It's just the Euclidean distance. So if the distance would then be defined between 2 points and two Euclidean vectors of dimension d, right? But in some cases, it's only defined by elements in the data set. Okay, so we can be a bit more general on the distance we chose. Okay, so we're given as input, and this is different than what we've been talking about before. The distance, this is we're assumed it's input here, right? So that means that in order to start with the problem, you may assume someone has, you've done modeling already. You've decided this is the right way to measure the distance between two data points. You say, if 2 data points are close, then this distance is small. This distance function will give you something small. If they're far away, it'll give you something large, right? And this is given to you as input, right? So this, either someone gives it to you and says, okay, in a homework assignment, use this distance function, or you decided this was the right distance for some reason, okay? But now this is input. And we're going to see that different algorithms we do will do different things depending on what this notion of distance is. Some algorithms require its Euclidean distance. Others require it's a metric. Okay, in some cases it doesn't require that. Okay, so this is the input. And now our goal is clustering. Okay, so the output here is going to be, we'll say a clustering of X is going to be a set of subsets of X. S1, S2, up to Sk. And these are going to have 3 properties. So we're going to say that each Si is going to be a subset of X. So it's a set of points that's going to be, and this defines the ith cluster. Right? So this is the ith cluster. Okay. 2, we're going to require, in general, that Si intersect Sj is going to be equal to the empty set. Okay, so this is known in generally, this is for I not equal to j. And so this is known as hard clustering. This is hard clustering. If you drop this requirement, otherwise it's called soft clustering, where if you don't, so the two subsets, if they can intersect with each other, this would be soft clustering. Okay, and then the third requirement is that if you look at the union over I of Si, this is equal to S1 union S2 up to union Sk, right? Then this is equal to X. So this means it's some sort of partition of the data. I've split the data into k different parts. Each of these is a cluster. Okay, so let's draw a little picture here. I could have some, and you'll see pictures that kind of looks like this, right? So maybe this is my input data set, and then I'm going to say this is S1, this is S2, and this is S3. These are my 3 clusters. They don't intersect with each other, right? The S1 is actually these 3 points. This is, right, for instance, this is a X1, X4, and X7, and so forth. And these 3 points make up S1. This is S2 and S3, and so forth, right? They don't intersect with each other. They're all subsets of X, and the union makes up everything. Okay, so that's, and there are k of them. This is when there are k clusters. Okay, so this kind of makes sense. So who's like heard of the clustering problem before? Okay, so this is not totally new to you. Most of you, who's not heard this before? This is kind of a new formulation. Okay, good. Okay, so this is, now, usually at this point I get someone to raise their hand and say, well, how about this? I know of a clustering algorithm that doesn't fit this model. Okay, sure, yes, there are versions that don't quite fit this model of what clustering is. As I said, there are many, many variants of it, but this formulation captures how in data mining, what you usually call as clustering, this is basically what they mean by clustering, possibly without this hard constraint. Soft clustering is not uncommon. There's different areas, so in like in some like parts of spatial data analysis, they'll say clustering finding is they're finding like a spatial anomaly of data. They're finding, they'll put like a bunch of data on a map, and they'll find some region which is abnormal, and they'll call that, and finding that region, they'll call that a cluster. That's a little bit different. When we get to the graphs part of class, we'll talk about a variant of finding subsets of graphs that looks like that. There are formulations like that, which are often called clustering, but that's a different class of problems. It's just a reuse of the name. Yeah.
What did you say was the difference between hard and soft?
Soft clustering does not have this constraint. It could say, it could add a data point. If I put a new data point here, right? I can say, well, this is partially in cluster 2 and partially in cluster 3, somehow. And somehow assign it partially to S3 and partially to S2. And then that would be a soft, then that would be a soft cluster. I'll mention a couple things about how you can extend things to soft clustering, but we won't talk too much about them. There's a technique called mixture of Gaussians, which was in the book for the undergrad pre-class for this that I could, that's kind of the most common form of soft clustering. I can give you links to that if you're interested. Okay. Okay, so this is clustering, okay, fine, but there are lots of ways of partitioning a data set into k different pieces, right? So this is not really, told us how do we use this distance function, right? I haven't really told you what the right objective is, although it usually follows this pattern. Okay, there's also some, so there's going to be some sort of, usually, some objective function. Right, so we'll say that some clustering is better than another one. We'll give it a score. We'll say this clustering gives a score, and we want the one with the lowest score. Right? We'll talk about some variants later that deal with this. Today we're going to talk about this hierarchical agglomerative clustering, which doesn't even try and do that. It just defines this procedure, and maybe it kind of optimizes something, but I'll talk about that towards the end of the lecture. So usually it says I'm going to try and do something that minimizes some distances someplace. Right? Okay, so let's try and be a little bit more specific here. There's kind of at a high level. So what is the objective of clustering? Okay, so I want to think of having kind of some set of points, and in the lectures I'm kind of forced to draw them into 2D, and then we'll think of the natural distance we're given. So typically we're given x is going to be a subset of R2, and the distance is going to be equal to just the Euclidean distance in between 2 points. Okay, so this will just kind of be like the default way of thinking. And this is a pretty reasonable thing to think about. If your data is 2D and your goal is to do clustering with Euclidean distance, you're probably better off just plotting the data and drawing circles on the piece of paper. And I'm totally serious about that. If you really need to automate it, we'll talk about something on Wednesday that will help you automate it. But you might not even want to trust that automation, and I'll try and tell you why. Right? You really want to use this when you can't really see your data that well. You're given some more abstract data like documents, and you define something like Jacquard distance between them. How do I do clustering then? That's a little bit tricky to draw them on a piece of paper and draw circles around them. Okay. But how do we think about what are the objectives? For that, it's fine to draw these pictures, right? So let's say we're going to have 3 clusters here, and this seems like a good set of three clusters. So we're going to think about 2 things about the objectives here. We're going to think about all of we want to look at the distances. I'm drawing these edges, but we're thinking about all the distances in between kind of different kind of objects which are in the same cluster. Right? So we're going to look at all of the d of xi and xj for xi and xj in, say, SL. Right, so say this is cluster SL. Right, so these are all the points in a cluster, and we're going to look at these distances, and we'll do something like the sum ij of d of xi, xj, or the max of d xi, xj, or the sum of this d xi, xj squared. You can think of variants of this. And this is kind of a notion called, at least I will call it in this class, the width. So you want to think of some notion of the width of a cluster, kind of how big are all the edges or all the distances within a cluster. And I want this to be small. So our goal is to make this, the width, small. Okay, so inside of a cluster, I don't want a lot of long edges. Okay, or I don't want any long edges, or only a few long edges, right? Kind of something like this. And I'm being vague because I want to be general at this point. Okay? There's another kind of way of thinking about an objective where we draw the edges or the distances. Kind of, let's look at all the distances in between two clusters. So now we're going to look at something, and we'll call this the split. And this will be including the distance xi, xj, xj, where we're going to have, this is going to be, we'll call this s, s, and this will be st. And we're going to say, look at all the distances for xi in ss and xj in st. Right, so I've got edges now going across two clusters. And I want to think about this for all of the pairs of clusters themselves, right? So within any one cluster, or all of the clusters, or all but a few of the clusters, I want the width to be small. And the split, I can measure this for all pairs of the clusters, right? And again, it can be the sum of the splits or the max of the splits. Or, I'm sorry, I want the split to be large, right? So this can be max over all I, j, s, t, dxi, dxj, or the sum I, j, and the max of s, t. I can do any sort of weird combination of these things, say of d, xi, xj squared, any kind of combination you want, and I want this to be, the goal is to make the split large. Okay, so these are kind of the two things. I want clusters themselves to be far apart from each other in some way, and I want the clusters themselves to be very compact, all the points close to each other.
Shouldn't that be a min then, not max, for the split?
Sure, it can be min, or it can be max.
Okay, you just can't choose.
Yeah, and so they're different formulations, and they do different combinations of these things here. These are just some examples. It could be, it could be the min. Yeah, I could say the min of ij over the max of st, or the max here, or the min here. Yeah, I mean, there's probably been 100 papers written on each thing you've thought about. So, okay, so, yeah. Oh, question? Or, sorry. Okay. No problem. Okay. Okay, so overall,
with clustering, with the width versus the split, if you're doing something like max and split, should you also do max and width, or can you trade min for max?
yeah, you can trade them off. There's not necessarily a right or a wrong answer. Throughout the next kind of few lectures, we're going to look at some of the most classic versions of these. Okay, so we'll see some examples of things that tend to have been popular. And we'll think about kind of if you make some differences to these within the different kind of classes of formulations, then you get different algorithms, and sometimes it leads to more efficiency or easiness to use, or you can say something formally about it, and sometimes it'll in terms of how well and fast it works, and then sometimes it'll have a modeling implication, right? And we'll think about these choices, but they're all viable choices at this point. I haven't given any recommendations yet, and so the overall objective is to is you want something like large, let's say, split divided by width, or we can say something like split split minus width. Think of something like this. right? Or it could be something else. So sometimes you only measure split or width, some version of it, and the other one is kind of optimized in the right way, kind of just by looking at one of the objectives. Okay, so there are a large variety of ways to try and model this. And if you think through them, some of them make more sense than others. Okay, so this is kind of a fairly vague and high-level kind of way of thinking about what is clustering. So we somehow want to use the distance to then come up with some formulation and then somehow optimize that formulation. Okay, except the first class of clustering algorithms we're going to talk about are actually, they're really just kind of these, so like I would probably even call them so just procedures instead of algorithms, and that they aren't really trying to do anything. They're just kind of, I'm going to tell you to do something and I hope it works well. Now there's recently been some analysis that says for some, you can retroactively map some objectives and say something about them, but that's not really how they were invented. Okay, and so let's start with this. So the topic today are this specific type of clustering called hierarchical. See if I can spell this. Hierarchical agglomerative. So clustering. And so hierarchical means that we're not just going to define this partition, not just this partition, but actually a hierarchy of partitions. So think of like a binary search tree has like a hierarchy to it. I split at the top into two parts and then so forth, splitting recursively going down. The agglomerative part, however, means that we're building from the bottom up. Agglomerative kind of means something like you're gluing stuff together. So I'm kind of gluing stuff together from the bottom. So think of like building a binary search tree where you build the subtrees first and then you keep gluing them together. And that's kind of the right picture to have here. Okay? And so so again, this is again a very general kind of set of procedures. And so I'm first going to describe it in an the algorithm in an extremely general way. So it's the algorithm is just if two points are close enough, then put them in the same cluster. Okay, so if I find 2 points which are close enough under some distance measure, let me modify this a little bit here. If 2 points, or I'm going to say clusters, are close enough, I'm going to merge them together into the same cluster. Okay, so I'm going to have a bunch of points. Right, so I'm going to start with a bunch of these points, and they're in the plane again. Right, and so what I'm going to do is say, okay, I found these 2 points, they're close enough, I'm going to put them in the same cluster. Maybe these 2 points are close enough, these 2 points are close enough. This point and this cluster are close enough, so I'm going to put them in the same cluster. This point and this cluster are close enough. These are close enough. These are close enough. And then maybe I stop, or maybe I say, okay. You know. And so the nice thing about this is you're getting this hierarchy here, where I've got, let me just call them by numbers. So I'm getting this nice hierarchy here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 1 and 2 are in the same cluster. 3 and 4 in the same cluster. I should have put 1 and 2 next to 5. let me just move these around a little bit. 5, 3, 4, right? 1, 2, and 5 are in the same cluster. I get a hierarchy here. This is cluster, and then 6 and 7 are in the same cluster. This merges with 8, 9 merges with these, and then I make this hierarchy here, right? So I get this nice hierarchy here, and then I can, if I want to say, well, I want 2 clusters, so then I chop off the hierarchy here, and I get these 2 subtrees, which correspond with kind of these 2 clusters here, right? So I'm not just getting 2 clusters, but I can, once I've pre-computed this, it's easy to figure out kind of clusters at many different levels of resolution.
Do we order the data randomly, or how do we order this?
Well, so the data is given to you as a set, so it has no order to it. And then you need to figure out how to cluster them, given the input as a set. And then to draw this, you probably want to reorder them so that you can draw a nice tree structure that way. Yeah. So if I had done 1, 2, 3, 4, 5 in the other order, I couldn't have drawn a nice picture. It would have overlapped. So I reordered them in this order so I could draw it nicer. And, so that makes sense to do. It kind of gives you an ordering, but there's a lot of flexibility. I can flip this whole subtree. I can do 1, 2, 5, 3, 4, 9, 8, 7, 9, 8, 7, 6, right? And it still looks like a nice picture. So it doesn't quite give me an ordering, but it gives me something kind of like an ordering.
So this looks like an offline model. Is there like an online variant of this?
So as new data is coming in, you want to update the cluster. Hierarchical clustering is tough for that. There probably are some algorithms for this. I'm not aware of at least ones that work really well. The next 2 kind of sets of types of clustering, the center base, which we'll talk about Wednesday, and the spectral, we'll talk about next Monday, they have some more online variants of this. Hierarchical, it's tough. Adding 1 new data point here might change the whole substructure here. I may have merged 2 and a new point 10 first, right? And then 4 and 2 and 10 may have joined, and then 1 and 3. And so the whole structure may change if I add 1 point. It's kind of more brittle somehow. So that's harder to do in online variant in this version. Doesn't mean it's not possible, but it's tricky. I wouldn't recommend it probably.
Can we just add the new point to the closest cluster if, as the question is saying that, and why do we need to restructure all the clustering? We can just measure the closest distance.
Yeah, okay, you could potentially do that, but you can come up so like your data keeps kind of, you keep getting more and more data points coming that keep looking like, like this. And what I keep doing, I keep adding them. I don't know at what level of hierarchy to add them, right? Should I add them to this whole big cluster here? Should I merge them with 9? Should I merge them with themselves before I merge them with something else? It's kind of, you get these issues, and ultimately I want to say something about how good is my hierarchy or the hierarchy at some level, and it's hard to say something for sure about this, right? Probably in a lot of cases this might work well, and then occasionally doing some sort of rebalancing. And probably someone has looked at this and kind of said what works well in practice and what doesn't. I'm not sure about that. So it's a good question.
So for those leaf nodes, do you need to sort them based on their distance, between each other?
Sort them based on their distance. Okay, so if they were one-dimensional, I could do that, right? I could look at the x-coordinate of all these points and I could sort them, and this would make sense to do it. Probably the x-coordinate ordering would probably look like this ordering. In 2 dimensions or in higher dimensions, like 10 dimensions or 1,000, 300 dimensions, or if I'm using Jacquard distance, I don't really know necessarily how to do that. What am I sorting them according to? I have pairs of distances, but I don't have I could look at all the distances from point 2 right? And then maybe I can sort them based on the order from point 2, but why don't I do the order from point 9 instead? I don't know. It's kind of, maybe that's a good way to start organizing your data. So, it's not necessarily a bad idea, but it's not necessarily going to help. So let me maybe we'll talk a little bit more specific about the algorithm, and then maybe we can ask more questions like this.
How do we calculate the distance between a point and a cluster? I mean,
Okay.
do we take the average?
So that's a good question. Good question. So, right. So how about I move on and specify this a bit more, and then we'll talk about some of the variants of this, right? And I'll point you to some of the most common variants. And yes, you have to define. I haven't told you how to define that yet. And this is, again, leads you to various variants of this. Okay, so let me write this out as pseudocode instead. So step 0 would say each xi in X is a separate cluster Si. So at the start, my initialization, step 0, I'm going to have n clusters, right? I'm going to have n clusters, okay? And then I'll say while and now I don't have data points. I only have distances between clusters, but when they only have one point in them, I know how to measure this. But now when 2 clusters are close enough, then typically what I do is I don't just pick anything. I'm going to say I'm going to find the closest to clusters Si and Sj, and then I'm going to 1b, I'm going to merge clusters Si and Sj into so a new cluster, and let's just call this, it can be Si again. So I have one fewer cluster than before. I've gotten rid of Sj, I now have Si again, right? And so this is the pseudo code for the algorithm. Okay, and there are 2 things that we haven't, there are 3 things we haven't talked about, or 2 main things. I need to decide what does it mean to be close enough, or So I have to have some notion of when should I stop? Should I complete the whole hierarchy or not? Or should I complete it and then decide what to say? And how do I define the closest pair of clusters? How do I measure distance between 2 clusters? Right? So, okay, so at this part, how to define a distance between Si and Sj, right? And so it could be that they're just 2 points, right? Each Si and Sj both contain a single point in them, and then we can use our original input distance. But if we don't have that, so then what should we do, right? How should we define this?
So it's like every cluster will have like a central point associated as, every cluster will have like a center of mass point, and then we can use that somehow.
So good. Okay. So the first class of solutions is to define a center. We'll call this Ci of each Si, and the same for Cj, Sj, and then use the distance between Ci and Cj. Okay? And so but then we have a sub-question, how do we define the center of a cluster? And so, right, this is a big class. This is a very good suggestion. There are a lot of variants that use something like this. But we need to define the center. And you had said, like, the centroid. So what do you mean by the centroid? What is...
Something, a point which has sort of like a maximum, a distance from all the points is maximized somehow, like.
Or is minimized?
Yeah, sorry,
Right, yeah. Okay, so let me say, they're kind of, what you're thinking of is the, you're suggesting the geometric, some median, and this is equal to the point you define CI is equal to the arg min of point C inside of the metric space that minimizes the so it's the point that minimizes, arg min is the point that minimizes all of the x in my cluster Si, the distance from x to C. So I want to minimize the sum of these distances. This is known as sorry, I wrote Euclidean distance here, but let's just say the distance, generically, the distance between x and C, right? So this is known as the geometric median, and it has a lot of nice properties. It's very stable and it's robust to outliers. It's not necessarily easy to compute. In 1D, this is exactly the same thing as the median of the data set. Even in 2D, for using the Euclidean distance, you cannot always compute this in a closed form. You can often approximate it pretty well, but I can't always compute this in a closed form. If I make a small change to this, something that's much more common is just to use the mean of the data set. Now, if I'm using if I'm using my distance as Euclidean distance, then I would set CI, which is it's going to be two things. It's going to be the R min of C in this metric space, and this, let's say this is going to be just RD, and this is the sum over all of x in SI, and it's going to be the distance from x to C, let's say Euclidean distance here, the Euclidean distance from x to C squared. Now if I minimize the sum of the squared distances, this turns out it's the mean, which is exactly 1 over the number of points x in SI x. So I'm just taking the average. If I take an average, this generalizes naturally to vectors. I can take the average of vectors element-wise, and that's exactly the point that minimizes the sum of the squared distances. And so this is a very common thing to use.
So this center is technically not a point of the data set, right?
Correct, yeah. Right, so this is not necessarily a point of the data set. We'll talk much more about these variants on Wednesday. But you can use these within this hierarchical framework. You can also say restrict. You can do either of these variants, restrict to some C that's a subset of SI. Right? And then for either variant, I can just test all of them and see which one minimizes some distance. Either the sum of the distances, or the sum of the squared distances, or the maximum of all. I want to minimize the maximum distance. Right? That's also a common thing. It can be minimize the maximum distance. I can also say the center of the minimum enclosing ball, right? This essentially kind of minimizes the maximum distance. And I can define this for any metric. I can define this. find the element which minimizes the maximum distance. That's essentially the center of a minimum closing point.
Is this for hard clustering or soft clustering? I mean, what happens if the...
So for variants where you're summing over stuff, with soft clustering, you assign elements into a cluster with a weight between 0 and 1. Right? So if it's 50% of its weight in here, then in this sum, I give it a weight of 0.5 in the sum. And also in the size, if I'm normalizing it, I only count 1/2 of that 0.10. So I can handle weights for these summed objectives. For max objectives, it's a little bit not as good of a fit. I can do it, right? But it's not going to be as good of a fit. This is probably a poor modeling choice.
We need at least 3 points to build a pole, to build a circle.
In 2D, in 1D you need 2 points.
What if
In 3D you need 4 points.
Okay. Let's say in 2D, what if the cluster has less than 3 points in one cluster?
Well, so I don't technically need it, right? Say I've got 2 points in 2D. The center of the smallest closing ball is right here, right? In kind of, for most cases, there are 3 points that define it, but I can always define with 2 points or 2 or fewer points. The same holds in general, in D dimensions, I may need up to D plus 1 points is enough to do it, but I can define the center with fewer than that. Yeah. There are algorithms for solving this approximately pretty quickly. It does have a closed form solution, so I can't find it. So, but you know, you can use different variants of this. Okay, but these are not the only ways to define this distance between two clusters. There are other entirely different ways, which don't involve using a center. Sometimes it's a mess to define a center, so I don't want to define it. Yeah.
You could just do like the distance between the closest points.
Okay. So yeah, so this is another good one. This is called this objective is called single link, and it's the distance between S and Sj is equal to the min over x in Si and x prime in Sj, and the distance between xi and x and x prime. Between x and x prime. Right, so this is called single link. It's the closest distance between points in the clusters. Okay, so this is a very popular one, and it basically, the only way, this gives you something which is kind of structurally fairly different than most other clustering algorithms. It'll be different than the center-based ones, which we'll talk about on Wednesday, and the spectral ones. And it will give you some sometimes kind of interesting looking clusters that you can find. The classic example is this, is what's known as the two moons data set, which looks kind of like this, where I kind of have these two sets of points. They're all very close to each other, one thing in each other, but their kind of regions don't intersect with each other. So I want to find one cluster like this, S1, and then another cluster like this, S2. This is called the two moons example. So you'll see this example on papers. I've never seen anything like this in a real data set. Okay? It's like, I mean, maybe people have searched all over to look for data sets that kind of look like this, and maybe I've seen one or two where they kind of force it, say, well, there are kind of these two subspaces I want to cluster, and they're not linear, and they kind of wrap around each other, but I'm like, yeah, I don't really buy that that really means those are two different clusters. So, but you can get this with this algorithm, the single link algorithm. You run it where you use this objective function, and you will find these two different clusters where just about any other algorithm will not find clusters that look like this. Okay, so that means that this particular version gives you some power which is different than other clustering algorithms. So this is one way where this choice will give you a different result than if I use like the Lloyd's algorithm for the k-means objective, which we'll talk about kind of Wednesday, or I use one of these center-based things. Most other algorithms instead will give you two clusters that look that will look instead something like, you know, like this. It'll try and do it like that. That's the typical. Most algorithms will give you something that will look like this instead, which is structurally different. Okay. Okay, that's kind of a neat example about how you can do something different with single link. I've seen plenty of synthetic data sets where someone created a data set to show their algorithm worked well, and they looked something like this. This is not uncommon, but in real data, I don't see that so often. Okay, how about something else of this variety? Right, without a center, other than looking at the min distance.
I guess you could do an average distance.
Yeah, right. So you can do. This would be called the average link, and this would be d of si sj is equal to, and it's going to be the same as the sum, right? So I'll just, you have some normalizing thing, where I then sum over all of x in si, sum over all of x prime in sj, and I look at x prime. Okay, so I want the average distance between all pairs of points in my clusters to be small. And if I just look at the sum, it's going to kind of make sure that the clusters don't get too large because I'm just adding stuff up. So the more points I have between them, I'm going to say they're not in the same cluster just because I keep adding stuff. But I want to somehow average it out. So I look at the average cluster. That ends up average distance makes more sense. Okay, and then kind of in this model, there's another common thing, the furthest link, and this is more kind of enforces that the clusters don't get too spread out, si, sj, and this is equal to the max over x in si, x prime in sj, the distance x prime. Right, so this furthest link, this will enforce that the clusters, if I merge two things together, I don't want anything to be too far apart. And you can think of modeling reasons for this. So I don't want any two things in my cluster. If I define the width of a cluster to be the furthest, kind of the furthest edge inside the cluster, I never want that to be large. And that's kind of my goal. And maybe I'll stop running the algorithm when all furthest links, any two pairs of clusters I try and join, something is too far apart. I set some threshold. I say, if any two kind of, I'm thinking about like any two houses are further than 5 miles apart, I never want to put them in the same cluster. So I will stop and I will keep merging clusters, and I'm trying to minimize the furthest link, and I will stop when I can't merge any more clusters. Right, so this would be a reasonable thing to do if you want to ensure that clusters are never too big in this sense. Yep.
So you can use furthest link in combination with the other two, right?
In combination with the other two.
You are just restricting the spread of the cluster with furthest link while you're clustering with single link.
Oh yeah, so I could go back to this function. I could say that close enough is defined by furthest link, but the closest is defined by the like on a single line. Yeah, this totally works, makes sense. You could say, I have some data set like this where I'm getting these manifolds or whatever kind of buzzword you want to call them that are kind of fit the data, but I want to find patches of these manifolds. So I never want it to be too big of a patch. Yeah, so you can mix and match these things. Right? Often, that's sometimes good. It's more common just to stick with one and set some threshold or build a whole hierarchy, but there are reasons why you want to mix them. Let me give one more class of things, and it's like these, but I want to say, I kind of want to have a score for a goodness of fit. So I want to define a goodness of fit of a model M and a cluster S. Right, and then I'll define some function M and S. And there's some goodness function. I want this to be large. Let's say I want it to be large, and it could be anything like the average distance from the mean, right? It could be something like that. But I could do a regression fit to the cluster, and if the goodness of fit of the regression fit is above that can give me a score. Right, so I want to say there's some model that describes all the data within this cluster. Okay, and this could mean a variety of different things. You use your imagination. People have used, I've had people in class use it to fit kind of like trajectories of people doing hang glide. Right, so it can mean a wide variety of things. And then I say the distance between Si, Sj is going to be equal to the goodness, if the goodness is a thing that is better when it's larger, then maybe, let me just say, negative of M Si union Sj. Right, so so I just used a distance. I said it was better or bigger, so I made it a negative. You can do that. I can do 1 minus that, something else like that. But I want to say I'm interested, and this model is derived from the data somehow. Right, so I want to say as long as I can fit a good enough model to two data points, then I will merge them together. And if I can't fit a good model to them, then I don't want to merge them together. And so this may end up having nothing to do with some inherent geometry of the data. It may be like I have customer data and I want to predict whether they're going to buy some, they're gonna buy some product, right? And if all the customers in some subset of the data, I can fit a model to this that does really well at prediction. It has good generalization error. Then yeah, let me merge them together into the single model. If I can't, if I merge together two data sets and I can't build a good predictor for it, then I don't want to merge them together. Right? So this is kind of, think of, you're building a hierarchy of classifiers, hierarchy of regression, and I can do this and use this hierarchical clustering framework in order to build this by using some very general notion of goodness of fit in order to determine this distance. Okay, and so this is kind of a pretty interesting modeling choice of your distance, but it will work. In this case, the distance does not need to be positive, it doesn't need to be a metric, but the algorithm will still work. Would you
try to use the same model for all of them, or are you trying to construct?
So the model, the model is going to be some function of the data. So I'm somehow going to fit a model onto my data here, and then I'm going to measure how good So I find the best possible model in some class to fit the data, and then I measure how good the best possible model is. And it could be a machine learning model, it will be some other things that we'll learn about it in the class.
So, in an extreme situation, we can like consider each data point as a cluster of its own and try to fit a model with other data points. But this will inherently be prone to problems like overfitting, or maybe it will become like a problem of exhaustive search.
Yeah, so I mean, okay, so if my goal was set, I want to find, like I set some threshold of allowable goodness of fit, and then there are kind of a few points you made I want to address, right? So if I said something like I'm going to define a regression and I'm going to measure the goodness of fit by a generalization score. So that means I'm going to do cross-validation, we'll talk about later in the semester, hold out some data randomly, fit a model on the data, and then measure it on the data I've held out somehow, right? And this gives me some goodness of fit. Because I've used generalization, I've used cross-validation, and if I'm careful about how I do that, it won't overfit. There's some things you need to be careful about. We'll talk about those later in the semester. So you can design it so it won't necessarily overfit the data. I think that's a separate issue of how you measure the goodness of fit. Right? If I'm just measuring kind of the sum of squared errors, it's possible. Right? Now, okay, how do I solve this? If my objective is to say, I have some threshold for goodness of fit. I want it to be, I set some threshold. This is above some threshold. Let's say the threshold is some arbitrary number 10. I don't know what that means, but I've set threshold 10. Then I want to find as few clusters as possible which satisfy this. You're right. That's a hard optimization problem. I don't know how to solve it. But I can run this algorithm, and it will probably work fairly well. Okay. This algorithm, for a general goodness of fit measure, not a lot is understood about how well this algorithm works. But for some, there's some understanding about this. I can talk a little bit about that now. So let me say something specific you can say about, sometimes this algorithm works well, and provably well, but you need to decide what you mean by what is a good hierarchy. I don't know, is there, before I go describe this as kind of the next step in the whole lecture today, did I answer your first question? Okay. Okay, so I want to say, like I said that there's going to be a single objective function that says how good is this clustering. And this is harder to do for a hierarchical clustering. Because I may have found, okay, these two satisfy that the maximum distance between any 2 points inside of a cluster is not too big. And maybe I can see if that's good. But is this the best clustering for that? How well does this work? And also, I have more information. I have this whole hierarchy. The other algorithms we talk about won't necessarily have the whole hierarchy to go along with it. How good is this hierarchy? Did I do well at the beginning as well? Okay, and so for a long time, like no one really said formally, how do I say how good is the hierarchy? There was a paper by Dasgupta in 2016, which had a pretty nice way of defining this. Okay, and so instead of a distance, it uses a similarity between points. And we'll say Sij is going to be equal to some similarity function between xi and xj. Okay, and then what his paper defined, it said some overall objective to a hierarchy, right? So now a hierarchy is going to look like one of these binary split, one of these binary split diagrams, where if I look at some kind of, I can define a cluster here, and that contains all of its leaf nodes, right? If I have a different cluster here, I get all of these leaf nodes. They aren't all at this same level, right? And these might overlap, right? If I look at this one here, it's this subcluster. Okay. So I want to say how good is this, and I have this similarity score between all pairs of the points. Okay, and let me see if I can write this down. And this cost, so find this cost of some hierarchy is equal to the sum over all xi, xj in the data set, the similarity between those two, right? So if they're more similar, this is a higher value. If they're more similar, I want them closer to the leaf nodes. I want them to be I want them to be paired up pretty quickly, right? If the similarity score is high. Okay, and so how I'm going to measure this is I'm going to multiply this by the number of leaves, and I'm going to say the hierarchy of I intersection j. Okay, so this hierarchy I intersection j, so this is the number of leaves in this. So this I intersection j is going to be the smallest subtree containing xi and xj. Okay, so let me say if I have, this is x1 and x4, then this pink subtree is hierarchy 1 intersection 4. Okay, and the number h1 intersection 4, this is equal to 3, because there's also x5 here. So this is equal to the size of the set x1, x4, and x5. Okay, so if something has a high similarity, I want that the size of the smallest subtree that contains it to have a small number of other nodes. Okay, so if things are far apart, I'm okay. So I need to basically have kind of n-1 of these different subtree nodes, these merge points, and I want to make sure I merge things that are similar to each other close to other clusters, and things that are far, the things with the low similarity, I want to wait till those at the end, because those are going to have like all of the leaves. Anything that goes across the green and the gray subtree, so any kind of pair that goes across there is going to have a large, then the number of leaves is going to be all of them. It's going to be all n, right? So I'm going to have some of those, but I don't want to have those. I only want to have small similarity. Okay, and so this is a pretty reasonable cost function. There's lots of things kind of you can say about it, and in particular for a lot of like the single link algorithm or the furthest link algorithm, these if I run that with this hierarchical agglomerative process, it tends to work pretty well. And in some cases, you can say it does pretty well at minimizing the cost.
So the lesser the cost is, the better the hierarchy is.
Right. Yeah. So then like the goal is to find h to minimize costs of H. Right? So I want to find the argmin over all hierarchies. Right? And okay, so in some cases this is a hard problem to solve exactly, but this hierarchical agglomerative process for certain objectives, depending on how I measure this similarity, they were often studied where it's given to you as a graph, so the similarities are 0 and 1. Then there's some cases where you can show that these algorithms do close to the optimal, depends on how you measure similarity. So there's been some recent work that says this is often a pretty reasonable thing to do. Okay, I'm not going to go into any more detail on that, but this is kind of a way of formulating this as a cost function, which I think is starting to catch on as the right way to do it. But again, this is only from a year and a half ago, right? So this is still, people have been doing this for a long time without really this guidance. And there's still a lot not understood about this, especially for more complicated sort of ways of measuring similarity. Okay, let's see. So, yeah, okay, so one more thing I want to mention, and then I want to talk about a cool high-dimensional fact that we didn't go over last week, Wednesday. Okay, so a number of you will probably do experiments with clustering for your project, and you'll have a homework assignment where you implement some of these clustering algorithms. Talk about the efficiency of this. In general, for these algorithms, how long did this general algorithm take? Right, so remember, it's basically find closest pair Si, Sj, merge Si, Sj. Right, so and then you kind of loop. All right, so how long does this take in general for n data points? N cubed, yeah. Right, so naively and in general, this takes O of n cubed time. Okay, so finding the closest pair, this itself might take O of n squared time. I may need to look over all pairs of these distances. Just measuring, it could be there's some objectives where actually this takes n squared time just to compute once, right? Imagine that both of Si and Sj have like 10% of the points, then this could be, I may need to compute all pairs of the distances. That's usually not a problem. We can often fix that. We can we don't need to recompute this every time now. The problem is this loop may need to go O of n time, and I need to find the closest pair. So I may need to check may have been O of n squared pairs I, j. Okay. So let's say I can often, even though this cost function, this distance between two clusterings, d of Si, Sj, I can often update this in, if on a merge, I can often update this update this in O of 1 time, or at least, or O of n time. So if I go from, if I have stored d of Si, d of Sj, d of Si, d of L and D of S, say, J and D of S, L, and then I merge SI, SJ into SM, then if it's like the shortest link or the furthest link, then I can compute D of SM, D of SL in if it's like the shortest link, then this could be something like min of SL, SI, and D of SL, SJ. Right? So I can often update this quickly. And also, I don't necessarily need to check all pairs of distances every time. If I've only updated SM, I just need to recompute the distance from SM to each of the other clusters. Right, so in order to do this, and then I want to find the minimum, and I can keep like a priority queue around. So you can often, sorry, I'm a little bit all over the place here, but you can often, with a priority queue, get this down to O of n squared times log n time, where I keep track of all the pairs of distances. I have to update n of the distances each time I do a merge. And there are a total of n steps in this process. And if each distance can be updated in constant time, then I have to do n log n to update the n distances, and I do that step n times as I do n of these merges. I get n squared log n. It can be as bad naively as n cubed or as n fourth, depending on the objective. Okay, but you can often speed this up a bit. Okay, this is still slow. Okay, so the other algorithms we'll talk about in this course are going to be faster than n squared log n. And it's not just like slow in an algorithm asymptotic sense. It's not going to scale well to large data sets. So just be aware of this. And you can get a lot more modeling flexibility than the other things we'll talk about, but it's going to be slow on large data sets. It's really hard to get past this n squared log n unless you make some assumptions about the data. Like if the data's in 2D, you might be able to do better with some variance of it. But often if your data is in 2D, I tell you plot it and draw circles. That'll probably work just as well or better. You don't really need to do this in 2D. Maybe 3 or 40, you might be able to speed it up using some ways, but then you're stuck with Euclidean distance and so forth. Okay, so I want to tell you one more cool thing about why KD trees break down in high D. Okay, let's just go through this for 5 minutes. Why do KD trees not work in high dimensions? Okay, so why don't they work in high dimensions? And it has to do with the this eternal battle between boxes versus balls. Okay, I don't know if you knew there was this big battle going on in high-dimensional geometry, but this is a battle that they were always facing when designing algorithms for them. And so we're typically talking about Euclidean distance, which is, draw it over here, which is the distance looks like a ball in some way, but we're somehow fitting this, decomposing the space into boxes, right? And so, let me just draw a particular ball and box understanding where, think of, we're trying to fit the biggest ball inside of a box, or find the box which best fits a ball. So it's going to be a square. Okay, and let me give you a particular set of parameters saying, say this is a ball of distance 1. So then we can think of this as being the origin and this is being 1, 1, this is being -1, -1, and so forth, right? So it's a 2 by 2. The distance here is 2, and the diameter of the ball is 2. Okay. Okay. So in 2D, it looks pretty reasonable. It's not too bad. There's some corners, but it's a reasonable approximation. What happens to the volume in high dimensions, in d dimensions as a function of d? Let's start with the volume of the ball, ball in d, of radius 1. The volume of the ball, you want to remember the volume of the ball in d dimensions? It's going to be, what?
Is it 4/3 pi r cubed?
Well, in high dimensions, it's a little harder. It's pi to the power d over 2 divided by what's known as the gamma function. It's uppercase gamma of d over 2 plus 1. Okay, so this is the volume of a ball of radius 1 in d dimensions. What is, times the radius to the power d. The radius was 1. Okay, so we can ignore, in the setting I have, we can ignore this term. What is the gamma function? It's a strange function, but when d over 2 or when the input to it is even, when it's d plus 2 over plus 1 is even, it's actually the factorial of 1 minus that. Right? So this is approximately, in every other dimension, this is exact. For the other dimensions, it's something weird, but it's pi d over 2 divided by d over 2 factorial. Right? So that's 1 times 2 times 3 times 4 up to d over 2. Okay? What does this number look like? Does this get bigger or smaller as d gets larger?
Smaller.
Gets smaller, right? They're both essentially, I'm multiplying d over 2 things together. The one on the top, each term is pi. The one on the bottom, the first couple terms are smaller than pi, but then they get bigger than pi, right? So this as d goes to infinity, this goes to, it ends up going to 0. Don't worry about how fast or slow it goes to 0, but it's going to be less than 1 for everything after something like d equals 5. Okay, for d, say, greater than 5 or 6, something like that. Yep?
Shouldn't the volume increase when the radius is 1 and decrease when the radius is half?
Yeah, so there's this radius to the power d going on, but I've set the radius 1. So let me just show you the volume, just to complete this, the volume of the box in d dimensions. Remember now, this is a box where the radius is 1, means the side length is 2, right? So the volume of this is 2 to the d. This was easier, right? Well, what happens as d goes to infinity? The volume goes exponentially, to infinity. It grows exponentially quickly, the volume of the box. Whereas the ball, it gets smaller. It's generally less than 1. Okay, so these are diverging really quickly. This is the best fitting box to a ball. There are other ways you can see this too, but in 2D, they're pretty close. But as I get to 5 or 6 dimensions, they start diverging, and by about 10 dimensions, the volume of the box is greatly larger than the volume of the ball. Okay, and so that means that if I fit a ball with the box, they're going to have very different volumes. The ball will contain a very small amount of what's in the box. And basically, you're going to have a lot of these corners, and the corners are going to be huge. Each corner is going to be about 1 over 2 to the d. I'm going to have 2 to the power d corners, and they're each going to basically contain that fraction of the volume. Very little of it will be inside the ball. So these corners will just get really big. So there's this tension between boxes and balls just kind of starts getting destroyed in higher dimensions, and so the notion of distance becomes kind of very sensitive, and this gets kind of weird. So if I'm restricting to splitting on the dimensions, I'm going to run into problems quickly. So that's why these data-dependent things have the potential to work better, and that they don't have this restriction. And they happen to work much better because they're splitting along the data sum. They don't quite face this challenge. Okay, cool. So we'll talk about these case center-based clusterings or center-based clusterings on Wednesday. So I'm giving you an example of the sort of questions that will be faced that you're going to have to do with jobs, right? You're going to get as the number of times